Okay, so this last example that we'll finish the section off with has a couple of things that set it apart from previous examples. The first one is that it involves trig, and that won't really change our approach. It'll just change how some of the details work out. But the other difference is that in this case we're asked to find all local extrema for a function on a given closed interval. So because we're restricting our attention to a closed interval, that's going to add one little difference, well actually technically two little differences when we get there, but I'll leave those for when the time comes. So for now we'll start this out in exactly the same way as we have for the previous examples. We're going to start by finding our critical numbers, and to do that we're going to need the derivative. So if you find the derivative of g of x, do it term by term. Derivative of x is just 1. Derivative of sine of x is cosine of x, so you're going to get 1 plus 2 times cosine of x. Okay, so that is your g of x function, or pardon me, g prime of x. So for critical numbers, we want to find when that is equal to 0 or when it is undefined. So g prime of x is equal to 0, well, when 1 plus 2 cosine of x is equal to 0. So solve that for, well, start by solving it for cosine of x. You're going to get 2 cosine of x is equal to negative 1. If you bring the 1 over to the other side. And then you're going to get cosine of x is equal to negative 1/2. Okay, well, when is that going to happen? And remember, we're only focused, there's an infinite number of values where this happens, right? Because cosine of x is a periodic function. If you do the graph, it just keeps going up and crossing the x-axis back and forth over and over and over again. And it will hit negative 1/2 as a y value infinitely many times. But if you restrict yourself to the closed interval 0 to 2 pi, what you'll find is this only happens at the values x equals 2 pi over 3 and 4 pi over 3. I'll leave it to you to work out the details, right? To solve this equation, cosine of x equals negative 1/2, you end up getting 2 pi over 3 and 4 pi over 3. Draw the unit circle, observe which quadrants cosine of x is negative in, and then use either the special triangles or the table to figure out a starting value. Figure out when cosine of x is equal to positive 1/2, and you can put all those ideas together to come up with this conclusion. Okay, so I'll leave the details of that for you. But what about the other type of critical numbers? Are there any type 2 critical numbers? Is this derivative ever undefined? Let's mention that. G prime of x is undefined when? Well, 1 is a constant, it's always defined. Cosine of x, that's an oscillating function, that's defined on the entire real line. Multiply it by 2, it's still going to be defined everywhere. So this derivative is defined everywhere. So there's no problems with points of singularity here. So when is g prime of x undefined? Never. So why did I even write that down? It's probably a good habit to write this out each time when you calculate your critical numbers. I haven't done it for every example, I'll admit, but I would actually recommend that when you're first starting these exercises out, just get in the habit of always writing out g prime of x is undefined, and then if it's undefined somewhere, you can write the values immediately after. If it's not undefined ever, then just write never. But what you're doing, if you do that, is you're setting yourself up to make sure you're always in the habit of checking for type 2 critical numbers and you don't forget and miss those. Okay, so, but anyways, we did get 2 type 1 critical numbers over here because those are places where the g prime of x was equal to 0, but no type 2, so let's just summarize our critical numbers. Our x equals 2 pi over 3 and 4 pi over 3. So I'll just draw a box around those. That's kind of your first challenge for these types of problems, is finding all your critical numbers. And once you have your critical numbers, the next thing you're going to want to do is to figure out, well, what happens in between those numbers. When is the derivative positive and when is the derivative negative? So what you're going to do now is do the first derivative table, and this is going to look a little bit different with this example than it did in the previous example. I'm just going to jump right to this table where we have a row for g prime and a row for g. So what's different from this example and some of the previous examples? Well, let me get out the previous page. On the previous page, we had a separate row designated for every factor of the derivative. Right? Like these were the two non-constant factors of f prime of x. We had listed them each in our table, but I skipped that this time because, well, how are you going to factor this? 1 plus 2 cosine of x. You can't really factor it. So there's not much to do except just roll up your sleeves, and we're going to have to do this manually just by plugging in points directly to the derivative. So, but in principle, this is the same. So here's what I mean. We'll start by labeling our critical number. That's why I did those two slices here, because we're going to have one for 2 pi over 3, and then the other one is 4 pi over 3. And we're going to pick sample points in between, just like we always have. Okay, so something, oh, and also here's a key difference. Because we're doing this over a closed interval, 0 to 2 pi, slide down a bit, over the closed interval 0 to 2 pi, we're not going to look outside of that interval. So whenever that happens, if you're working in a bounded region like that, I like to just do this. Put 0 here and 2 pi here, just to remind yourself that those are kind of as far as you're going to go. So that when you pick a point to the left of 2 pi over 3, make sure you don't pick something too far to the left, right? Pick something to the left of 2 pi over 3 on the number line, but make sure it's still greater than 0. Okay, so that's what we'll do. So how about pi over 3? Because we want to make sure that it's less than 2 pi over 3 and greater than 0, but it's also got to be something that we can reasonably plug in to g prime of x. We're going to have to plug this into cosine of x. And at least in principle, I'm showing you how to do this by hand. So you don't want to pick pi over 7 or pi over 5 or pi over 10, because those are tougher to work with. Okay, so that's why pi over 3 is a good choice, because that's one of your fundamental angles. Now, between 2 pi over 3 and 4 pi over 3, well, that one is a little nicer. We can just pick pi, because pi would be 3 pi over 3, right, which is right halfway in the middle between 2 pi over 3 and 4 pi over 3. Something between 4 pi over 3 and 2 pi. Think of 2 pi as 6 pi over 3, and then take the midpoint again, and you're going to get 5 pi over 3. And that's a number that we can reasonably plug in to cosine as well. So that'll be good. Those numbers will work. But now, instead of just doing this just by looking at it, we're probably going to have to actually do a little bit of work here. So let's actually plug each of these sample points into g prime of x. So, and I'm going to draw a dividing place here, because this was the work to find our critical number. So I don't want that. I want that to stand out as being separate from what we do below, because now we're going to evaluate the function g prime at each of these sample points. So g prime of pi over 3, that's the first one. Well, g prime of x is 1 plus 2 cosine of x. So we're going to have 1 plus 2 cosine of pi over 3. Okay, well, pi over 3 is a half. So this is going to be 1 plus 2 times 1/2. 2 times a half is 1, so this works out to be 2. Okay, well, let's work out, or I guess let's fill in the table. This is the funner part. That's positive, so that means this is going to be positive, which means our function g is increasing on the interval of x values between 0 and 2 pi over 3. So now let's plug in pi. So g prime of pi, we're going to get 1 plus 2 cos of pi. Now cos of pi is -1, so this is going to be 1 plus 2 times -1, which is actually just 1 minus 2, or -1. So what is that? That's negative. That's all we really care about. So we got negative, and that means our function is decreasing between 2 pi over 3 and 4 pi over 3. And then lastly, I will plug in 5 pi over 3. So g prime of 5 pi over 3, well, that's going to be 1 plus 2 cos of 5 pi over 3. Okay, so again, the reference angle of 5 pi over 3 is just pi over 3. But you have to do a quadrant analysis to determine the sign. So cos of pi over 3 is a half, but based on the quadrant that 5 pi over 3 lies in, this is going to end up being, cos of pi over 3 will end up being positive a half as well. So I'll leave the details to you. There are some details to check there, but they are a bit of a distraction from the main flow of this problem, so I don't want to get bogged down with them. I want to just focus on the main ideas. So I'll leave it to you to check the details here, but cosine of 5 pi over 3, that's a section 1.2 calculation. You can refer to that section for some reminders, but you'll end up getting positive a half there. So you'll get 1 plus 2 times 1, positive 1/2, which works out to be 2. And in particular, all we care about is that it's positive. Okay, so that tells us that we have a local maximum at 2 pi over 3 and a local minimum at 4 pi over 3. So let's work out what the y coordinates are. So now we're going to plug these into the original function. So g of 2 pi over 3 is going to be, well, what was the original function again? Let's remind ourselves. G of x is x plus 2 sine of x. So g of 2 pi over 3 is going to be 2 pi over 3 plus 2 sine of 2 pi over 3. Okay, so now what's sine of 2 pi over 3? Well, the reference angle of 2 pi over 3 is pi over 3, and sine of pi over 3 is root 3 over 2. And based on the quadrant that 2 pi over 3 lies in, draw the unit circle. I'll leave it to you to do that. Sine of 2 pi over 3 is also going to be root 3 over 2. So this ends up being 2 pi over 3 plus 2 times root 3 over 2, which ends up working out to be 2 pi over 3 plus root 3. Okay, so that was our local max. Now let's work out g of 4 pi over 3 and find the value of the local minimum. So g of 4 pi over 3, we're going to get 4 pi over 3 plus 2 times sine of 4 pi over 3. Okay, and then this is getting a bit squished here, so I'm just going to draw a dividing line there. 4 pi over 3 plus 2. Now sine of 4 pi over 3, reference angle of 4 pi over 3 is also pi over 3. But based on the quadrant that 4 pi over 3 lies in, sine of 4 pi over 3 is actually going to be negative. So this is going to turn into negative root 3 over 2. So we're going to end up with 4 pi over 3 plus 2 times negative root 3 over 2. And this is going to end up being 4 pi over 3 minus root 3. So that is our local minimum. Now, technically, we also have a local minimum at x equals 0. Because if you just look at the graph near this area, it starts here and then just starts to go up. So if we just look at this area, whatever this endpoint is, right at 0, 0 is going to be the location of a local minimum. Could even be the absolute minimum, but it's definitely going to give us a local minimum. And then at the other endpoint, 2 pi, looks like we have an absolute maximum here. Because I mean, you can imagine the function goes something like this, right? But then it just hits a stopping point. So as it's coming up and just stops abruptly, that's going to be a local maximum. Because if you restrict your attention to just this part of the graph, this is going to look like a maximum here. So 2 pi is going to be the location of a local max. And again, it could be the absolute max, but that's besides the point. The important part is it still is technically a local max. So let's work out those values as well. G of 0, so that'll be 0 plus 2 sine of 0. Well, that just sine of 0 is just 0, so you end up getting 0. And g of 2 pi, well, you're going to get 2 pi plus 2 sine of 2 pi. And sine of 2 pi is also 0. So we're just going to get 2 pi plus 0 here. So you'll just end up getting 2 pi. So now we finally have everything we need to summarize our answer. So let's do that at the bottom of the page. We have enough room here at the bottom. So let's start with our local minimums. So therefore, g of 0, which is equal to 0, and g of 4 pi over 3, which was equal to 4 pi over 3 minus the square root of 3, those are local minimums. Right, just looking at the table here as a reminder, we've got a local minimum here at 0, and we've got a local minimum here at 4 pi over 3. And then the other two critical numbers ended up giving us local maximums. So g of 2 pi over 3 which was equal to what? That was equal to 2 pi over 3 plus root 3 over here. And g of 2 pi, which was equal to 2 pi, are local maximums. And that is your full set of local extrema in this case.